So thank you for that wonderful introduction, and thank you also for inviting me to Dublin. So my grandfather was actually born in Ireland. I'm Irish by nationality. Brexit has made us look at our ancestors and go and get new passports. My grandfather left Ireland 100 years ago, and it's very nice to kind of come back and actually see where he was born. First time I've been in Ireland. So indeed, I'm going to talk about black holes and quantum computers. So one of my affiliations is the University of Southampton, and the other is the Alan Turing Institute, which is actually the UK's Data Science Artificial Intelligence Institute. Somewhat strange as a theoretical physicist to be asked to join this, but it is actually coming from these connections with quantum computing that come out of studying black holes. So this talk is going to be exploring kind of very surprising relationships between the mathematics and fundamental physics, so the very theoretical aspects of black holes, and what could ultimately in the future be the next generation of technologies. Now, I'm a theorist, this is not a technology that we're going to have in the next few years, but it's setting the sort of foundations for technologies that we will develop in the future. So just as quantum mechanics in the 1930s, at that time it was a very abstract, very theoretical topic, but it's essentially responsible for everything that we're doing in this room, or the technology in this room. So these kind of considerations may be responsible for the technologies of the future. So black holes are something which almost need no introduction. Everyone in the room has some expertise in black holes, and they know that we have really black holes. So black holes appeared in science fiction around the time that people really started taking them seriously in science. There had been work before this period, but it was really in the 1950s and 60s that people started to kind of take them seriously as possible astrophysical objects. And the terminology and concepts that you see used in science fiction have their roots within science. There's often overlap. I myself, I'm a scientist. I love sci-fi. I love the Marvel Cinematic Universe. I may not like all the physics in it, but I really love it. And I think this wonderful interplay between science and sci-fi is great at popularizing sort of really wonderful concepts coming out of science. So as I say, you're all experts. Now, the movie on the left-hand side, I wouldn't particularly recommend going and seeing it. It's not the best of movies, but I highlight it because its name, the event horizon, that's a concept that's in science, and the event horizon plays an important role in this movie. On the top right-hand side, you see a very famous picture from Interstellar. I'll tell you a little bit more about that later. So Interstellar, it's fair, I think, to say, without spoiling the plot for anyone who hasn't seen it, that the black hole is one of the big characters in that movie. And the consultants on this movies were people like Kip Thorne, who won the Nobel Prize for the discovery of gravitational waves, so real experts in black holes. Well, I'm British, so I love Doctor Who. Doctor Who, when they get bored of the Cybermen and the Daleks, they have been known to send a TARDIS into geostationary orbits around black holes. So they will use this, and they will use interesting concepts of time running differently in different parts of spaceships as well. So you have some sense of what black holes are. Now, quantum computers. We're really only going to touch on notions of quantum computers in this talk. So I really only need this very simple cartoon picture to explain to you why quantum computers could be important in the future. So the entire basis of what your classical computer that sits on the table, sits in the chips that sit in our phones, the basic notion is that it stores information in binary form, and then it performs operations that individually change each of these binary numbers. So you take your 1 and you change it into a 0. The basic idea of a quantum computer is that you store your information, again, in binary form, but you store it in a way which is entangled in a complex way, and then you can perform operations with your quantum computer that don't individually flip each of the digits, but simultaneously operate on a very large number of digits. And the system can store information not just as zeros and ones, but as things which are in between. Now, I like this cartoon. I didn't draw it myself, but I like this cartoon because I think it captures something of the spirit of why a quantum computer has potential. You can kind of see that this idea of simultaneously operating on many pieces of information and maneuvering them, manipulating them, how this could potentially be faster than working with a classical computer where you're working on a basis of actually individually manipulating each 1 and each 0. And so the idea is that at least for some processes, a quantum computer could be much faster than a classical computer. It can use the wonders of the quantum universe, the wonders of quantum entanglement, to actually work with things faster. But this talk is not propaganda for quantum computing, because quantum computing clearly has many challenges. You will see many optimistic articles in the press which talk about maybe having a quantum computer in 5 years, 10 years, 15 years. But there are really many, many challenges. I'm a theorist and I don't work on most of them, but let's just talk about what they are. So designing and building the actual computer. So at the moment, most of the quantum computers that sit in labs involve something like 40 or 50 atoms. We would need to scale this up to billions to actually have something which stored as much information as our laptops. And so this is a challenge. So scaling up prototype systems, designing and building them. Now, what I described to you on the previous slide of doing manipulations where you simultaneously operate on different pieces of information, that sounds great. But then you can say, but hang on, what goes wrong if I accidentally spill some coffee on some part of my quantum computer? So I didn't just mess up that part of the computer's hard disk, because everything is all stored in this complicated, entangled way. Did I kind of screw up everything? And that's a kind of simple example of the problem, the basic problem of controlling, the operation of a quantum computer. This entanglement is very, very subtle. What happens when it's interacting just with the environment around it? So most of the prototype systems are sitting there in clean room labs, and we have to be very careful in how we deal with them. My kind of, my thought experiment where I'm actually tossing my coffee onto my quantum computer, that brings up the issue of error correction. So we have to, again, worry about the fact that we stored information in a very complicated way. What if we messed it up in some part of this? How do we actually correct for that error? How do we have redundancy of information? And another very basic question, I kind of said to you in a vague way, well, maybe a quantum computer could be faster, but what would it be good for? What kind of software would I want to run for it? Do we really want our favorite web browser to run that much faster? Is there something that we could do with it? And that's, again, a very big question which many people pursue. What would we actually want to do with a quantum computer? So this talk is not really about any of these, most of these very big problems. It's actually really linked to the fundamental theory underlying quantum computers. So I said to you that in a lab, we are working with systems which have sort of 30, 40, 50 atoms at most, so a relatively small number of atoms. And we know we need to scale this up to billions. So how would we describe this? What would be the mathematics that we need to describe this? The mathematics that we're using for 20 or 30 atoms is not going to work so well for billions of atoms. And what I'm going to say at the end is that the kind of mathematics that comes out of understanding black holes could be relevant to understanding scaled-up quantum computers with large numbers of degrees of freedom, a very different way of looking at the theory of quantum computers. So I'm now going to go back to black holes and tell you what is a black hole. So what's the basic definition of a black hole? So this really comes from Einstein's theory of relativity. So we're going back to the beginning of the 20th century, where Einstein told us that nothing can travel faster than the speed of light. So if we throw something off the surface of the Earth, we know that there's an escape velocity. If we throw something sufficiently fast, it will escape off into space. But if we take the same mass that we have in the Earth and we squash it, so we increase the density, then the escape velocity increases. And if you make it more and more compact, more and more dense, the escape velocity gets larger. And so eventually, as you squash things down and down and down, you could say, well, it seems like you could form an object for which the escape velocity is larger than the speed of light. But then nothing can travel faster than the speed of light, so if not even light can escape, that's what we would call a black hole. So this is actually a very old idea. Whenever I give this talk, people say, no, you haven't got it right here. These ideas go back much earlier. But certainly two of the references which are often quoted, so there's one from John Mitchell in 1783, there's one from Laplace. Laplace, of course, very famous, very well known. People who study mathematics or engineering will know his name from studying Laplace transforms and so on. So both of them had the idea that you could have stars for which gravity was so strong at the surface of the star that not even light could escape. But at the time people were playing with these ideas, people didn't understand the propagation, the movement of light. That came with Maxwell in the 19th century. And they certainly didn't understand strong gravity. And so really our mathematical, our conceptual understanding of black holes comes when Einstein writes down a theory, a horribly called general theory of relativity. But essentially what this is a theory which describes gravity when it's a very strong effect, gravity for things which are moving, close to the speed of light. So this is around 100 years ago. So almost immediately after Einstein wrote down his theory of general relativity, people realized that there could be black holes, that these were possible in the theory of relativity. But at that time, people didn't take this tremendously seriously. They thought, they were mathematical constructions, but they weren't physical solutions. So even the very famous sort of Schwarzschild solution, which was found almost immediately after Einstein wrote down his theory, was something which for some time people thought was just a mathematical construction. But there's a nice picture that comes out of Einstein's theory of what is going on around how you can visualize what's going on with a black hole. So the basic idea of Einstein's theory of relativity is that the force of gravity is caused by the space-time, the space becoming curved. So something which is heavy curves the space. And so, when we sort of demonstrate this in sort of open days at our university, what we have is a kind of rubber sheet, and we have some sort of marbles on it, and the marbles of different weight. And so these pictures you can kind of visualize this way. So visualize the sun as a marble placed onto a rubber sheet. So it kind of dips down and it bends the sheet. And so the sun is something which is a heavy object. The gravitational force of the sun, the force that actually the planets around the sun experience, can be sort of understood as the sun curving the space around it. Nowadays, we understand that the sun is only one kind of star. There's a complicated life history, evolution of stars. And so different kinds of stars can be more dense. In particular, stars which are later in their lifetime can become much more compact, and they can accordingly curve the space around them more. So things like white dwarfs, neutron stars. Again, the basic picture here, we don't need the details of them. The basic picture is simply that they've got the same kind of mass as our sun, but they're actually much, much smaller. So in the case of a neutron star, this is something which is so dense that you could kind of put the whole mass of the Earth within a very, very small sort of ball. So these curve the space around them much more. And so you can see that if you throw something off the surface of this star, you have to throw it that much harder to get it out. So this visualization, it almost ties to this picture that we have of throwing something up in the air, and we have to throw it very hard to get it off the surface. So in the case of the neutron star, we have to throw things that much harder, that much faster to get it off the surface. But neutron stars, white dwarfs, the sun, they all emit radiation. We can actually see them, we can capture them on telescopes. But then if we imagine keeping on going and making a star which is even more dense, then we get something for which there's a point, a surface of no return. And this is where this vocabulary of the event horizon comes in. So you see that it's shown on here. So as soon as you go deeper into that throat from the event horizon, even if you realize you've made a mistake, you turn around your spaceship, you can boost it up to the speed of light. You will still not be able to get out again. So everything which is deeper inside cannot escape. And so this is a visualization of what it means to be a black hole. We'll come at the end to the sense that actually, with modern ideas, we think that maybe this picture is not quite right. This is a picture which is based on classical physics. And at the end of the talk, we'll talk about how quantum physics could actually slightly change the picture of what's going on in the black hole. So still, we're going to have the feature that there's no light coming out of the black hole, but there'll be interesting quantum things going on too. So once people realized there were mathematical solutions to the equations, they kind of explored them to some extent, but it was really only in the second half of the 20th century, as I said, that people started to take seriously black holes as astrophysical objects. So it's after the discovery of the pulsars, neutron stars, that we realize that there are all these kind of exotic stars, and we start realizing that we could actually genuinely form black holes from the evolution of ordinary stars. Now, most of this talk, I'm going to be interested in black holes which have the same kind of mass as our sun. So these are the ones in the middle here, which are called stellar. So they come from, typically from dying stars. They could be formed through things exploding, through supernovae. The estimate is that there are probably millions of these in our galaxy. Another interesting type of black hole is things which are called supermassive. A self-explanatory term, really, because these are things which are millions of times as heavy as the sun, and they exist at the center of galaxies. They seem to be related to the way that galaxies developed and galaxies evolved. You can also have very, very small black holes, so-called primordial black holes. These could have formed very early in the universe, and these would be the size, the typical mass of an atom. So different types of black holes. So again, without sort of thinking about the details, let's sort of talk about why would you form a black hole. And this is something which was realized in the 1930s by Chandrasekhar in particular. So again, it's coming back to the idea of a life cycle of a star. So what's going on in an ordinary star like the sun is that we have nuclear reactions going on. And the basic equilibrium in our sun is that you have nuclear reactions going on, which creates a pressure, and that balances out. So that creates a pressure which would push outwards. But that's balanced out by the fact that everything has gravitational attraction. And so you've got a kind of a relatively stable or a stable object with a stable kind of size. But then what basically goes on as a star dies is that, just as the Earth is running out of its oil, its gas, so in a star, you run out of material to have nuclear reactions. And in a dying star, the basic thing is that there's no more nuclear fuel to burn, and so you lose the pressure of the nuclear reactions. And then what happens is that the star collapses under its own gravity. Now that's the simple argument that Chandrasekhar gave, and it's basically saying that gravity in the end always wins, it's attractive. If there's no other force around, it's going to win, and it's just going to pull everything inwards. Actually, the life cycle of a star is quite complicated. That's sort of shown a little bit on the left here. And we don't entirely understand all the details. We're learning a lot about this over the last few years by discoveries such as gravitational waves. And I'll come to that in a moment. So you could say, well, okay, so this thing is black. Black means that it's not giving out radiation of any kind, radio waves, visible light, X-rays. So if it's not giving out radiation, surely you can't see it on your telescopes. So how do you know that it actually exists at all? Okay, so it's really, again, in the sort of 1960s, 1970s that people start working on this. In the 1960s, you've got the discovery of the pulsars, the realization that there are really exotic kind of stars out there. There's also simultaneously an explosion of sort of theoretical work on black holes. And people started to look at that time a lot more seriously for black holes. So people would usually quote that the first black hole that was discovered was in 1971, Cygnus X1, and it's shown in this constellation above. I'll tell you in a moment how people figured out it was there. Now, how good is the evidence that this was a black hole? Well, in 1974, Stephen Hawking bet Kip Thorne that Cygnus X1 was not a black hole. Why did Stephen make that bet? Well, he just spent the last 10 years of his life studying black holes. So his logic was that if you kind of discover that this thing is not a black hole, it's some kind of star, all the thing he'd been doing for the last decade was wasted, then he at least wanted to win a bet. I believe that what was bet here was Playboy magazines. Neither party here, Stephen nor Kip, is not particularly politically correct about such things. But Stephen conceded in 1990 that the evidence was really just so robust that this was something which was a black hole, as predicted and understood in Einstein's theory of gravity. So how do people figure out that there's a black hole there? Well, for this I'm going to actually not tell you about the case of Cygnus X1, but actually show you a picture of Sagittarius A star, which is a supermassive black hole at the center of the galaxy. So it's about 4 million times as heavy as our sun. And it was discovered a little bit later, so this is 1974. The picture on the left is a little bit later again. So this is from the 1990s. By now there's much better data, but this data already shows what's happening. So again, it's the point that gravity is always there. So, even though the black hole is not giving out any kind of radiation, radio waves, or X-rays or anything like that, It's still a very heavy, very dense object, a very strong gravitational force. And so what one sees on one's telescope is the motion of stars in the vicinity around something. So you don't see the white star, you don't see this directly on your telescope. What you see as you watch for a few years is that things seem to be moving in orbits. And you can figure out from their orbits where the thing is in the center. So you can pinpoint exactly where it has to be, and you can also pinpoint how heavy it has to be. So you can figure it out from the shapes of the orbits. So it's almost like, even if the sun wasn't actually giving out light, even if we didn't have access to that, we would actually be able to, if we could trace the motion of the planets, we would actually figure out that the sun had to be there, exerting the force that it is, and we could figure out how heavy it is. Now let's go back to this picture. So I promised you black holes are black. So why does Interstellar show you a picture with these bright rings of light around it? So this is a picture which was almost certainly touched up for the movie and made beautiful by graphic designers. But ultimately, it is actually based on real physics calculations by Kip Thorne and his collaborators. So what it's showing to us is the black in the center, so the two black semicircles of the black hole. But then there is radiation around the black hole. So what's going on there? Well, the point is that black holes are it's not really true to say they're entirely black. We can see evidence for them on our telescopes if we can kind of just get enough resolution on the telescopes. So we said that black holes are extremely heavy. This means that if there's anything in the vicinity, in the neighborhood of the black hole, it's going to be attracted to the black hole. And it's actually going to be pulled in really, really fast. So it's going to be pulled in, and it's going to typically move around, rotate around, and be spun around really fast. But now if you pull it in and you spin it around, if you've got things which are charged, they're going to give out radiation. And so many black holes, or most black holes, are surrounded by something called accretion disk. So this is the disk which is shown in the center in this graphic, in this artist's impression. So this is material which is moving very, very fast. It's moving so fast it's been ionized and it's giving out radiation. Black holes also have typically very strong magnetic fields around them, and that is believed to be responsible for the fact that they have jets coming out of them. So they have streams of matter which come out at a right angle. So the black hole is spinning around and the jets come out at an angle to the disk. Now again, the black hole itself is black. So if we zoom in this picture, as you see in the sort of the top right-hand side, if you go into the very center, you see this little black dot. So that's where the event horizon is. So if you go really, really close to the black hole, it's still true that there's a region where no light is escaping. But in the immediate neighborhood of the black hole, you've got all of this light. So now let's go back to this picture, which was drawn by Kip Thorne. So in this picture, we've got an accretion disk. So the black hole is in the horizontal, the plane, we've got an accretion disk, and that's where the light is coming from. I should say, real black holes is not necessarily visible light. They might emit X-rays and radio waves. This one here, they're showing as emitting visible light. So it's got an accretion disk. So then you say, well, why is there a vertical ring as well? Why is that happening? Well, I think this is something which is, I'm sure it had been realized, but it hadn't been entirely realized before Kip Thorne and his collaborators did their simulations. The point is that the force of gravity around a black hole is incredibly strong. And so the light from behind the black hole, so there's an accretion disk, a ring around it, but the light from behind the black hole as it comes out is being dragged back towards the black hole, dragged inwards. And so that's what's responsible for the vertical rings. So if you got close enough to a black hole which has got an accretion disk, this is what you might expect it to look like. A little bit confused by the fact that, of course, again, many black holes also have these things which are called jets, and that the jet could actually mess up the vertical ring. But again, if you could get a good enough resolution, this is what you would actually expect to be able to see. Okay, so now Sagittarius A star. Why was it on my picture that I didn't see any detail about this? Well, it turns out, for reasons which are not entirely understood, even now, Sagittarius A star happens to be a little bit atypical in that it doesn't have a very a lot of accretion. It has relatively low accretion, but it actually does give out, it's got some amount of an accretion disk, and it gives out radiation in the radio wave band. And so if we zoomed in on my picture that I showed you before, so where we'd actually figured out that there was going to be a black hole, if you zoom in, you can actually see the traces of the accretion disk. And one of the goals of the Event Horizon Telescope is to actually get an image of Sagittarius A star at very, very good resolution. So we see much more features in this. Now, when I gave this talk sort of a few months ago, I would have to explain to people what is the Event Horizon Telescope. Now there's a lot more awareness because the Event Horizon Telescope has recently reported its results. So this is not the scientific results which have been shown. So the left-hand side is showing you what they're trying to do. So they're using a combination of radio telescopes on Earth to get very, very good resolution of astrophysical effects from quasars to black holes. The right-hand side, again, is not observational results. These come from simulations, theoretical simulations. So the top right-hand side is the image, the expectation of what kind of image they could get for a black hole with an accretion disk. Not a jet, but an accretion disk. So that was what they were trying to aim for. The bottom right, that's the kind of the resolution they would expect to get for something that's got jets. Okay, so that was what they were trying to get. What they actually managed to get is shown on the next slide. So this is not Sagittarius A star. This is actually M87. This is the first image that they've released. So this is, I think it's always great when things, I don't myself directly work on these black holes, but of course work on the theory of black holes. It's great when this appears on newspapers. It's the front page of newspapers. A couple of weeks back, this was the front page of the newspapers. So this is the image that the Event Horizon Telescope managed to get. The Event Horizon Telescope is an ongoing experiment. This was, in a sense, a proof of concept almost, and they've actually managed to do what they wanted to achieve. So again, the black dot in the center is the black hole itself, and the red and the yellow is zooming in and starting to get an image of the accretion around the black hole. And as we go on over the next few years, we expect these images to get better. We'll get the images of Sagittarius A star getting better as well, and we'll start to see more and more features of black holes. So that's observational evidence for the black holes. And so the picture I just showed you is the first direct picture, really, of the black hole at reasonable resolution. But the most detailed evidence for black holes really comes from the discovery of the gravitational waves experiment. So 2015, LIGO announced that they had discovered gravitational waves. So they announced 2016, sorry, the collision was in 2015, observed in 2015. So the first black hole collision that they observed, this was a collision between two black holes. These were quite heavy relative to the sun, 30 to 60 times as heavy as the sun. And they could figure out from the signal of the gravitational waves that the collision took place about 1.3 billion years ago. And the gravitational waves which were created during the collision had 3 times the energy of the sun. I don't mean 3 times the energy that the sun gives us every minute or every day. I mean 3 times the entire energy of the sun. So a really drastic cosmic event, right? Black holes coming and smashing into each other, releasing in just a tiny amount of time huge amounts of energy. And it's that, that in a sense, that dramatic nature, which means that we can actually still see the signal of this 1.3 billion years later. So again, this is something where a couple of years ago one saw the images on the front pages of newspapers. But before I show you the images, let me show you a simulation to get a sense of what's going on. So in this simulation, we're not looking at details about the accretion around the black holes. Those aren't relevant here. What we're following is just the 2 black dots in the center. These are the 2 black holes. And what we're showing is a simulation of solving Einstein's very complicated equations for gravity for these 2 black holes spinning around and then colliding with each other. The blue ripples that you see are expressing the ripples of space. So that is the effect of the gravitational wave. It's rippling, it's stretching and squeezing space itself. And the signal that you would actually see on your detectors is what is shown in the bottom. So you see they're spinning around each other, they're moving relatively slowly here. But as they get closer, they're sort of speeding up, and the space-time is starting to ripple more and more. The movie slows down because we're going to start getting more features of it. They're getting it again closer and closer. You see the space is dramatically curved, and now they've merged. They're one single black hole. And now you see just pulses and pulses of energy being sent out. It's, again, a very drastic process. All this energy is pumped out in a very, very small amount of time. So as I say, this simulation is by a large group of people, so Caltech and other places. So what was seen, so it's quite remarkable actually, given the difficulty of these experiments, the sensitivity that you need in your detectors to actually measure these gravitational waves. If you look on the left-hand side, we're looking for effects which are 1 part in 10 to the 21, 10 with 21 zeros. So we're designing experiments and setting up experiments which are that sensitive. So there are 2 detectors. One is, nowadays there's more, but at the time this measurement was made, there were 2 operational detectors. One was in Washington and one was in Louisiana. You need 2 detectors because you need to be sure that what you're seeing in your detector is real. It's not coming from just seismic effects, earthquake effects in the region. You want to be sure that this is actually something which is a real signal coming from space. And so you see here, even by eye, you can be pretty much convinced that, on the top part of the slide, the 2 signals and the 2 detectors look the same. They're slightly shifted in time, so the signal hit, the wave hit the second detector at a slightly different time, and that's commensurate with the fact that the wave was moving at the speed of light. Now, if you compare that shape of the signal to what you would expect, so what I showed you on the previous slide, from solving Einstein's equations for gravity, from the behavior of 2 black holes smashing into each other, the shape of the signal I showed you on the previous slide, again, even by eye, you can see that this looks like what was found in the detector. If you have experience of sort of doing more detailed analysis, you have an engineering or applied physics background, you can actually kind of break this down into the frequency decomposition, and you can see that, again, again by eye, that the frequency decomposition between the 2 detectors matches very nicely. Now, a really fun thing is about gravitational waves when we talk about, when we try to get people to understand what gravitational waves are. It's a really hard thing to understand gravitational waves when you talk about stretching and squeezing space. So one way to kind of think about what would happen is, if there was a gravitational wave that came through this room that had a large enough amplitude, it was loud enough, your ear would actually be able to hear it. So the waves that actually hit that detector were in frequencies that your ears can hear it. The problem is that the amplitude is so small, 1 part in 10 to the 21, your ear isn't sensitive. But actually, if you crank up the amplitude, you would be able to hear it. And a fun thing is that when we play these signals as audio signals, the sound of black holes colliding is very different from, say, the sound of neutron stars colliding. So different kinds of processes which create gravitational waves have different sounds. And we have great fun, actually, with kids when they come and work with us, getting them to listen by their ears and actually figure out, is that a black hole colliding or a neutron star colliding? It's amazing, your ear is remarkably good at seeing when the signals actually, detecting the signals and figuring out what they sound like. So this is now going to play the sound of black holes colliding. So we call this a chirp, and we give the kids, when they go home, we give them a whistle that actually makes a chirp. We get them to tell their parents that when black holes collide, it sounds like a chirp. It sounds like a chirp because the frequency goes up at the end of it, and so it's the frequency rising, the pitch rising at the end that makes it sound like that. As I said before, we've learned an awful lot in the last couple of years from these direct detections of black holes. So we had all this indirect evidence for black holes before this time, but this direct detection of the gravitational waves has taught us a lot. One of the first surprises was that these black holes were so heavy, 30 to 60 times as heavy as the sun. Because I already told you this idea that somehow black holes, surely they mostly form from things like the sun, as it dies, as it runs out of nuclear fuel. And now we've sort of started to understand much more how black holes, many different ways that black holes can form. How many black holes with these kinds of masses can they exist? What kinds of ways can they form? So it's amazing, even this one detection actually taught us very new things in astrophysics. There are many big astrophysical questions. So my group in Southampton works a lot on these, and they wouldn't like just my 4 questions. They put another sort of 20 or 50, many big questions. The accretion disk and the jets. Sagittarius A star, we still don't have very good images. So what do they actually look like? I told you we could figure out how heavy Sagittarius A star is, but actually we still haven't figured out entirely how fast it's spinning around. We know it's spinning around, but it's quite hard to pin that down. An open question. So far from gravitational waves, it's been fantastic. We've learned a lot about black holes. We've also now detected neutron star collisions. We've learned a lot about, we've learned things about neutron stars. We've confirmed theories about neutron stars. But there's still a big open question. Are we going to learn something really fundamentally new from gravitational waves, something we actually hadn't thought of before? And the question, when I talk about things like the Event Horizon Telescope, so as these images get sharper and sharper, the question is, does Einstein's theory actually describe what's going on at the event horizon? So again, as we're getting closer and closer, we're testing more and more what Einstein's predictions for black holes are about. And so for the last part of the talk, I'm going to move into the questions which actually theoretical physicists think about a lot, which is, really the structure of black holes, the quantum physics of black holes. So this poor astronaut, what happens if you fall into a black hole? I once wrote an article for The Conversation, which is a sort of, I guess, a media site with articles by academics. And the editors put a title of, "What would happen if you fall into a black hole?" And for the last 3 years, I've been getting an email a week by people asking me about falling into a black hole. So some people also write to me and say, "I'm really not worried about falling into a black hole. I'm more worried about losing my job," which I think is a reasonable thing to do. Okay, so what happens? And so this is almost one of the defining questions for us as theoretical physicists. What happens? So if we use Einstein's theory, I've already, in a sense, showed you what's happening is that the space is becoming, there's almost a throat of the black hole, you're almost falling down into it, you pass the point of no return, you don't really notice that you did so until it was too late. What you would actually see is kind of weird Doppler shifts, so if you've got light, you see it kind of very, very distorted. And then as you fell deeper and deeper into the black hole, well, the Einstein's theory would, and the work of Stephen Hawking and others would say, well, you're basically screwed because there's such strong forces, you're just going to be ripped to pieces. Okay. So why are we so interested in black holes? So Stephen Hawking, I would say, from 1974 onwards through the rest of his life, really spent 40-odd years thinking about what goes on inside the black holes. So we've been talking about the astrophysics, the fantastic astrophysics that's going on just outside a black hole. But here we're talking about what happens once you've passed that surface of no return, shown in orange here, once you've gone deeper into there. Okay, so why are we so interested in this? The point is that as you go deeper and deeper into the black hole, there's a region where the space itself becomes so curved, so, the forces become so strong, that the classical description, Einstein's theory, brought together gravity and relativity, but it's still a classical theory. And that's a region where Einstein's theory, classical theory, becomes invalid. So it's one of the, at least 2 situations in the universe where we know that we need to understand the quantum nature of gravity. So one is inside black holes, and one is at the very beginning of the universe itself, because at the very beginning of the universe was very, very small, very, very tiny, and we similarly need to understand the quantum effects of gravity. So really, the modern perspective, this is at least one thing that theoretical physicists can agree on, is that there must be very significant quantum effects which are coming into play at the event horizon. And I choose my phrasing very carefully there, because there are different ideas and different discussions about the details of what's going on, but we know that there must be, quantum physics must play an important role. So how do we know this? And again, this goes back to work in the 1970s. So you could have kind of complained when I showed you this picture of black holes, of simulations of black holes and the signal for gravitational waves. You could have said, but hang on, what kind of black holes did you collide? How did you form those black holes? What was the past history of black holes? But it turns out that, even though black holes can certainly form in many different ways, we know that they all seem to be described by the same, relatively simple if you're a theoretical physicist, they're relatively simple solutions of Einstein's equations. And so if you take a black hole which is heavy and spinning, there's a solution which was discovered by Roy Kerr in the 1960s. You go to the textbook, you look it up, and that describes any black hole which is heavy and spinning. It doesn't care about the details of how that black hole formed. So it didn't care about what kind of star it was in the past, it just knows it's a black hole. So this was known, this property was known in the 60s and 70s. Now, Stephen Hawking's perhaps most famous discovery was in 1974. So he discovered that when you take into account quantum physics, black holes can give out, they can radiate particles. Okay? So that's not a contradiction with what I've shown you before. So if we just took into account classical physics, we would say nothing can escape from inside the event horizon of a black hole, so the black hole looks completely black at the center. Now we're saying that if you take into account quantum physics, then actually black holes can give out particles. Not a contradiction with what it said before, because the rate at which it gives out these particles is very, very low. So a way to think about this is, suppose that you had a light bulb which was very, very dim. So as you kind of take a dimmer switch, as you lower it, there's a point at which you can actually no longer see that there's light coming out, because the emission rate, the rate at which the light comes out is so slow. And so this is what's going on with black holes. So the inside, it's definitely true, I'm not cheating in my earlier pictures, definitely true that the surface of a black hole, the event horizon of a black hole, still looks black. If you could sit around for millions and millions of years, hundreds of millions of years, and sit there with a detector capturing every single photon of light that came out, eventually you would actually have captured enough particles and you would say, hang on, the black hole did give something out. But if you're just looking at a snapshot in time on a telescope, it will look black. Okay, so it gives out, when we take into account quantum physics, it gives out black particles. Now this is a picture which Stephen liked to show of a sort of intuitive way of understanding Hawking radiation. So in quantum mechanics, the vacuum, the empty space is a peculiar thing. So particle pairs can pop out of the vacuum, they can appear, and they can disappear. Okay, and this happens all the time around us. This is a feature of quantum physics. Now, the basic idea in Hawking radiation is, well, what happens if you make this particle pair so close to the black hole that one of them falls into the black hole before it can kind of annihilate with its partner pair? And as it falls into the black hole, a funny feature of the black hole is that the particle that falls in effectively has negative mass, so it decreases the mass of the black hole, and then the partner pair has no longer got anything to annihilate with, and it escapes off to infinity. Some people love this analogy, and it's incredibly helpful for them, and some people hate it. So if you hate it, just put it out of your mind. But again, some people find it a useful way to understand what's going on with Hawking radiation. One thing I like about this is simply that it makes very clear the fact that we have to worry that there are quantum effects which seem to be associated with the surface of the black hole itself. There's some genuine sense in which the Hawking radiation, the whole phenomenon, is associated with the surface of the black hole, the surface of no return of the black hole. Now, this gives us a conundrum. So it's, when this was first posed by Stephen in 1974, it was almost like a philosophical question of how many angels can dance on the head of a pin. It seemed kind of to be almost irrelevant to physics experiments. But it's nonetheless a conceptual question which is incredibly important. Okay, so you have a black hole, You don't care how it formed, you've got a black hole. And now you throw away, you're clearing out the old offices and you throw away your obsolete computers into that black hole. And on those obsolete computers stored in the hard disk, they have your old thesis and your old notes and everything else like that. So they've got what we could call information. You throw this into the black hole. But now, according to the standard paradigm, the black hole only knows, the only information in the black hole is how heavy it is and how much it's spinning. Okay, that's all the information that's in the black hole. And now the black hole evaporates slowly. So you wait for millions and millions of years, and it evaporates, and it turns into a bath of heat. And the bath of heat only seems to know about how heavy the black hole was and how fast it was spinning. Now, this is what Stephen called an information loss problem. Because at the end point, all we got is this bath of heat that knows about how heavy, how much energy there is, and how much spin there was. But at the beginning of this, we threw in our computer. And our computer, my old computer, contains different things to your old computer. And so somehow, I should be able to figure out what was thrown in. So this is an information loss problem. We can never determine from what happens from the bath of heat at the end, we can never determine the history of the black hole, how it was formed. Now, when you give this talk, the first thing that people say is, aha, well, quantum physics, huh? There's something going on in quantum physics. Now, this is not true. This is something that's beyond quantum physics. So it's certainly true in quantum physics that there are some questions that you cannot answer with certainty. But that's because you're asking the wrong question. So the famous picture shown on the right is, of course, Schrödinger's cat. You cannot know whether the cat is dead or alive until you make the measurement. So you're asking the wrong question. You could only ask the question, is the cat alive, after you've actually opened the box and you've made the measurement. But built into our understanding of quantum mechanics is a notion of determinism, is a notion that if I know the state of the universe at one time, I uniquely determine the physics, the state of the universe at a later time. Similarly, if I can measure things now, I should be able to, at least in principle, work hard and figure out what happened at earlier times. So that's determinism. Things uniquely determine what happens at later times. And what's going on in information loss is actually worse than this. It implies that black holes are actually not deterministic. So again, if we know the state of the universe at the end, so this is almost like, again, black hole, Doctor Who, the end of the universe, right? The universe is sort of turned into a bath of heat. We cannot figure out from that the earlier history of the universe. So we really have a determinism problem. And again, whilst this might seem almost a philosophical and esoteric issue, it's so fundamental because it says that somehow a combination of quantum physics and gravity seems to be doing something very strange. It seems to be suggesting that the universe is not deterministic. And we as scientists, we rely that it is. That the universe is sufficiently complex that we may not in principle be able to calculate things. There may be questions because of quantum physics we cannot ask, but still there are things that we can actually predict and measure in the future based on what we do today. So again, why do people focus so much on this? It's because the lesson of physics is that when you find these paradoxes, these puzzles, these are the clues for what is the new physics. So when we go back to the beginning of the 20th century, the emergence of quantum physics, this was a paradigm shift. And it was a paradigm shift that came from an analogous paradox. So the paradox at that time, people had this image that we had, the structure of an atom, you had positively charged things at the center, you had negatively charged electrons moving in orbits around the positively charged center. And people couldn't understand with classical physics why the positively and negatively charged things wouldn't attract each other. That's what we learn, right? Positive, negative charges attract things. How could it possibly be stable for negative things to stay in orbit about a positive thing? And the resolution was in quantum physics that things had to be in discrete energy levels. That was the paradigm shift that was needed to understand atoms. So here, this understanding this puzzle, is to try and understand the nature of black holes and of combining quantum physics with gravity. So it's back to the drawing board. I'm not always a great fan of Big Bang Theory, but I must say as a physicist, it's always great to see what's on the whiteboard there. There's kind of, hidden Easter eggs, hidden jokes for people there. So it's back to the drawing board. There's a big idea that's missing. And over the last 20 years, we've really understood, or we think we've understood at least part of what the big paradigm shift actually is. So it was really ideas in black holes which led to a revolutionary new idea. So this is called holography. It's not the holography we're used to in sort of lasers. It's a different concept. What we're saying here is that gravity itself is captured, is described by a theory without gravity in one less dimension. So I don't think one can complain that this isn't a big paradigm shift, right? This is saying that the gravity in this room, the gravity in this room with 3 dimensions, that somehow we can understand this by thinking of a flatland theory with just 2 dimensions and no gravity. Or it's saying that we can understand that, the physics of the world, the physics of happening in CERN. We can understand this in terms, again, of something which is, something which is, in a sense, associated with a surface in one less dimension. So a very, very challenging, very difficult concept. So this was an idea which came about, as I said, by thinking about black holes about 25 years ago, by Gerard Prof and Lenny Susskind. But while I'm going to show you pictures in this talk, this idea became very, very concrete. We have very explicit mathematical ways to describe this, thanks to Juan Maricena about 20 years ago. So it became something which was really very, very precise. We can actually say, what's the description of gravity in one less dimension? So what does it mean for black holes? So, it tells us that physics really is deterministic. There's nothing wrong with determinism. Physics, quantum gravity should be deterministic. But then it suggests that what's going on at the event horizon, Einstein's concepts, Hawking's analysis of this, cannot be quite correct. So the picture that I'm drawing on the right-hand side, we're very used to drawing this picture as physicists, but actually it can't quite capture everything that's going on. And there's emerging consensus that what's going on is that the region around the horizon isn't quite what we thought, that we have to take into account quantum physics there. So there are various ideas about how to do this. This is one idea that's being explored. I like this particular picture. Not the details of this particular proposal, fuzzballs versus other proposals. I like this idea, this particular picture from the New Scientist, because I think it captures kind of correctly the idea that quantum effects at the surface of the black hole, the very, very surface of the black hole, are important. So those of you who are sitting at the back of the room, this picture looks like all the pictures that I've been showing you of a black hole. For those of you sitting towards the front, you can see that there's kind of fuzzy structure, fuzzy detail. And that's what the artist is trying to capture, the fact that there's some kind of quantum uncertainty, there's kind of quantum fluctuations going on here. So in these kinds of pictures, it's sort of saying that there are kind of quantum effects close to the event horizon, maybe just after you cross the event horizon, but you have to take into account these quantum effects. Now, people have various ideas of visualizing this and understanding this. Some of these are a little bit heuristic, but I think they're quite useful to get a sense of what's going on. So one interpretation is that you can think of the event horizon itself as behaving as a giant kind of quantum computer hard disk. So we're used to thinking about a hard disk as being something which is kind of flat, but imagine it as kind of a spherical surface. And now, for every little bit of area of the surface, we can store one quantum bit of information. But now we're storing one quantum bit of information for every Planckian unit of area. So a Planckian unit of area is tiny, and this means that we're storing a huge amount of information in a black hole. So if you take a solar mass black hole, the amount of information that can be stored in it is about 10 to the 50 of the laptop computer that I have in front of me. So it's a huge amount of information. And so the idea is the following. So this was drawn for us actually by a graphic artist. So he's married to one of the students in our group, and he likes to visualize the ideas. So again, it's perhaps not got all the physics in it, but it's kind of giving you a sense of visualization of these ideas. So this question we come back to, what happens as you fall into a black hole? So I said to you that the traditional perspective is that as you fall into the black hole, you cross the horizon, you kind of notice some weird Doppler shifts and lights and so on. And then as you go deeper and deeper into the black hole, you get stretched, you get squeezed, you have tidal forces hitting you, and you get ripped to pieces. And these ideas, what's going on is that somehow as you fall in, just as you cross the surface, there should be effects which is essentially turning your information into quantum information. So the zeros and the ones that you see here are the fact that the black hole is keeping track of you as you go in. So it's not like the original picture I said of something that goes into the black hole. All that's kept track of is the mass and the spin. No. There's some sense in which the black hole is keeping track of this information, but in a very, very quantum way. So I also have a sort of simulation of this progress, which actually indicates that the zeros and ones, they're kind of very quantum, right? They're fuzzy, they're entangled with each other. The poor astronaut, I think this is almost like the famous picture, the scream, right? The poor astronaut is somehow realizing what's happening to them as they go into the black hole. So we don't understand everything about this. There's certainly a lot more to understand. There's various different kinds of understanding of the way in which the information is kept track of as we go into the black hole. But I think there's some consensus at this point that indeed the information which is, as you fall into the black hole, this is kept track of. Eventually, if you fall into one, we should be able to find out what happened to you. But it should take us probably hundreds of millions of years to do so. So it's going to be a long time before we get that information back again. So now let me come back to the what I was talking about at the beginning. So relation with quantum computers. So the sense of an object falling into the black hole, we can think of this as something falling in is changing, the surface of the black hole is acting as a quantum hard disk, and something falling into it is effectively changing the state of the quantum hard disk. Now, I also said to you that black holes have enormous amounts of information. So we're talking very, very large amounts of information in qubits, 10 to the 50, 10 to the 60 qubits, enormous amounts of information. And we've got a mathematical language for describing what's going on here. So we can mathematically analyze thought experiments which are implicitly involving huge numbers of quantum bits. And what people are trying to do with this is to learn about quantum algorithms, particularly quantum error correction, from this kind of setup. So it sounds very counterintuitive that we want to understand the behavior of a computer, so we'll throw something into a black hole. We'll do a thought experiment of throwing something into a black hole. But again, this is actually giving us insights into quantum error correction in a context where it's not a toy model with a small number of atoms, but it's actually a situation where we have huge numbers of bits of information. And it's a different mathematical language than people have traditionally been using in the quantum computing community. So certainly building a Dyson sphere to use the black hole as a quantum computer lies in the realms of science fiction. So Freeman Dyson actually comes from Winchester, which is very close to where I live. So Freeman, of course, a wonderful physicist, scientist, mathematician, a Renaissance man in all ways. He had the idea that, many years ago, that one way to look for advanced civilizations would be to look for a civilization which had managed to build a sphere around its star to collect and harness all the energy of it. Now, again, the idea of this to actually harness a black hole as a quantum computer lies in the realms of science fiction. I had this on a slide a couple of years ago, and there actually appeared a science fiction story after my talk, which actually did this. But actually, these thought experiments can indeed, I think, give new insights into new ways of thinking about quantum computing. There are many challenges of quantum computers, but this would give a very different way of understanding things like correcting errors, dealing with large numbers of qubits, different mathematical language. So, to summarize, I've talked about several different aspects of the black holes. So there's huge excitement about the astrophysics of black hole, what's going on outside a black hole. as we get better and better images of the horizon using the Event Horizon Telescope, it's going to tell us much more about the black hole. Eventually, over the coming decades, it's going to be able to test theories which predict deviations from Einstein's theory. But at the same time, by thinking about black holes and studying black holes, this is actually, we hope that eventually this will help us understand things back here on Earth. And so, you know, all this picture, so on the left-hand side, you can see all these experiments, the gravitational wave experiments based on Earth, the space-based telescopes, and so on. They can actually help us with quantum computers. So on the top right-hand side, this is sort of prototype quantum computers. And a few years ago, I mean 10, 15 years ago, people would have said, well, it's completely crazy to be discussing quantum gravity in the same context as discussing quantum information, quantum computing. And actually now, there are, you know, people working on both fields do come together. There's a great collaboration called It from Qubit, which actually brings people together. The picture shown in this logo is actually imaging the behavior of things falling into black holes and relating that to quantum computing. And so, to conclude, I mean, it's a very exciting era for black hole physics because not only are we understanding astrophysics, but we're also at the point that we have new insights into the fundamental science of black holes, and this could eventually give us a better understanding of quantum computing. Thank you. I'll stop there.
You're describing the fuzziness of the quantum system at the event horizon.
Yeah.
So just wondering, before you pass the event horizon, would that fuzziness be, would it be possible to check that prior?
Okay, so now you're getting into the details of whether you think we think that the fuzziness is happening just outside the event horizon, or whether the event horizon itself is not as sharply defined, maybe that's quantum and fuzzy, or whether you have to just go into it. And I would say that that's something that people are exploring. So, you know, different people have slightly different takes on this. People are exploring that. If it was actually just outside the event horizon, then you could hope that ultimately you would be able to detect it. But I have to say these effects would be so small, we would expect them to be so small. This is the quantumness you would not be expected to be able to get in current generations of experiments.
You can tell me that the question makes no sense, I don't mind. But the figures for the two LIGO black holes, about 100 solar masses collide and about 3% become radiation. Were they from Kerr, the figures? Or were they completely different to Kerr? The Kerr figures on black hole size and rotational speed.
Yes. So this is all based on Kerr black holes.
It is.
It is all based on Kerr black holes.
That's what I thought.
And so, you know, so now as we start accumulating with the LIGO catalogue more and more events of black holes, people are actually starting to be able to pin down, is the Kerr black hole the best description? People have ideas of sort of modified gravity theories, and they start to test whether there could be modifications. But right now, Kerr black holes are, you know, seem to be a great fit for the data.
Thank you.
Certainly the simulations are based on Kerr black holes colliding.
Just a small parochial correction. The first person who calculated the image of a black hole, including the light which comes from the back, was not John Thorne, but John Lytton Sink.
Okay.
Yes. In a paper in the 1960s.
Yes, I should say that. I mean, there's, I absolutely, and it should be there. I think absolutely the calculations are there. It's the visualizations which Kit added. It was almost perhaps revisiting existing calculations, right? Yeah,
Would the fuzziness be more observable the smaller the mass of the black hole?
Yes, indeed. Yes. Yeah. But I should say again, I would not to be misleading. We would expect that this fuzziness is really so small for the types of black holes that we're observing using LIGO or using the Event Horizon Telescope. I mean, the Event Horizon Telescope, of course, is imaging supermassive black holes, so correspondingly, quantum effects are even smaller. But we would expect this to be so small that, you know, we have to get clever and think about ways that we might be able to detect this in 20, 30, 40, 50 years. it's not at the scale that we would actually be able to, we would expect to be able to get it now. I have to say, you know, we're also always in realistic systems mixing up the astrophysics as well. So you have to, and nobody is anywhere near thinking about these things. So if you had a smoking gun of a very atypical state of a black hole, so it's almost like it's in a state where the quantum state is like almost all ones. That would be a kind of analogy. It's very atypical. The effects could be sufficiently large that we might be able to detect it. And there are some people who kind of play around with, you know, phenomenological models about this, but actually, to be realistic, I think it's something that we don't expect to be able
Do
to
you have
detect.
any idea what those effects would appear so that we could look for those signals?
So people do some, in a sense, basic modeling of this. So Steve Giddings in California has been somebody who's been doing this. His underlying assumption is that these effects are quite significant. So in particular, if we look at, say, the orbits around the black hole, there's some stable orbits around the black hole, and he's having to assume that that these quantum, these non-local effects would affect these at, say, of order 10%, which I find very unrealistic. I think it would be much, much smaller effects. But at least in terms of the mathematical modeling of what kind of effects it could be, he, together with astrophysics colleagues, has looked at those kinds of effects. And with the kind of, the Event Horizon Telescope pictures coming online, people have started exploring that a bit more. I and my colleagues in Southampton, so I'm a theorist, I have colleagues who are working on the LISA experiment, which is gravitational waves in space. We're actually sort of starting also to model modifications to basically the gravitational wave signal that could come from modifications, quantum effects at the horizon. But again, theoretically it's interesting, but I think it's something which the effect I would expect to be sufficiently small that we're looking up far into the future to actually measure it. Yeah.
How could we observe a smaller black hole? Smallest observed?
So, okay, so now you're getting into the population of black holes. And again, I'm not an astrophysicist.
Sorry, I'm multiple.
I'm not an astrophysicist, so I'm not an expert. There doesn't seem to be a continuous population, right? So there are black holes which are roughly the same mass as the sun, and then there are black holes which are sort of 10 or 100 times the mass of the sun. There are these supermassive black holes, and then there's atomic-sized black holes, but there's not a continuous kind of spectrum. There's not a continuous sort of range of masses. So people have various ideas about how you could explore the possibilities of atomic-sized black holes. People have even suggested that they could be responsible for the dark matter. They've looked at ways to test that. They seem to, I think at the moment, rather robustly excluded that possibility. But that's something you could do. But the kind of question of saying, okay, suppose you took something which is 100th of the size of a black hole, 100th the size of the mass of the sun. I don't believe, maybe Nima or others can correct me if I'm wrong, I don't believe that we expect there to be black holes of that kind of mass. We don't see a mechanism for those to form, and so people have not really explored those or detected. Is that a fair statement? So we're interested in atomic, but not really full range, because we just don't see how they would actually form. So people do sort of think about, scattering from black holes, but your basic problem is that the gravitational interaction is just so weak that, again, we can kind of theoretically set it up, but it's not something which seems to be observable, any time in the near future. It just seems to be such a small effect that we would struggle with actually observing. Any further questions? Yes.
Yes, right. Can gravitational waves scatter, in the bounce off something in the same way that, the ripples of the river Thames can bounce off the wall of the river?
Right.
And my question, I'm more interested in understanding if the gravitational wave that we already detected some years ago can bounce off something coming back and giving us information about the things that they bounce ahead.
Okay, so I think the simplest answer to this is that gravitational gravitational force is quite weak, right? So any kind of interaction of gravitational wave tends to be weak. So how can we observe these signals from 1.3 billion years ago? You could say, well, didn't they smash into all kinds of things? So, you know, as they pass through the history of the universe, but we're really saved by the fact that effectively the gravitational interaction is so weak, and that's, you know, so actually trying to use them in the same way that you use electromagnetic waves. So you're already talking, you gave the example of water waves, but, you know, of course we use electromagnetic waves, you know, light all the time to probe things, right? But we're really relying on the fact that the electromagnetic interaction is much, much stronger than gravitational interaction. So whilst in principle you could do these things, in practice, again, the rate of interaction would be suppressed. And of course, it's a crucial factor in the fact that we are able to observe these gravitational waves from events which occurred such a long time ago. It really is the fact that they were effectively travelling along and not interacting, you know, that they were preserved. And all that happened to them in the history of the universe is that as the universe expanded, they effectively, the wavelengths got stretched. But we're sort of seeing a relic of something which was created such a long time ago. Right at the back.
I was thinking about a question regarding how the timing we are estimating, like we said, like when the gravitational wave was like created 1.3 billion years ago. How did you get the estimate of that timing?
Okay, so I've almost answered that question, the answer to the other question. So it's the fact that one way to pin it down is the fact that the universe is expanding. And so as the universe expands, your wavelength actually gets stretched. We understand the expansion of the universe very, very well. We've got very precise measurements of it. And so by looking how much the wavelength has gotten stretched, that's how we can figure out when this event occurred. So that's the basic mechanism of how we do it. Now, another thing you could have asked is, so how do we figure out where in the sky it came from? And that's why it's important to have even more gravitational wave detectors. So I said we needed two because we wanted to be sure that this was an event that wasn't coming from the Earth. We wanted to think it came from space. But as you start to get more and more detectors, by using the different times at which the wave hits the different detectors, you can figure out more precisely which patch of the sky it comes from. So already now we have a third detector online, so that's the Virgo detector. So with 3 detectors, you can get a much more precise direction from which it came from. When the next generation detectors come on, so the India detector, the Japan detector, we'll be able to pin down in the sky much more precisely where it comes from. And then for black holes, you don't see any counterparts on your telescopes, but if you see gravitational waves coming from neutron stars, you do actually see, at the same time as you get the gravitational waves, you should also see in your other telescopes things hitting. You should see, you know, just electromagnetic radiation hitting, and then you can kind of correlate this. So I didn't talk at all here about the neutron star collision detections, but, you know, correlating the gravitational waves with electromagnetic radiation, so-called multi-messenger astronomy, you can just put all this information together and pin down much more sharply where the event happened, when it happened, and so on and so forth.
I don't see any other questions, and I think we should probably finish this evening, but I would like to thank Marika again for a really fascinating talk and for leaving us, I think, with lots of exciting new ideas to think about as we go home. So thank you very much.